Number 9. Really interesting problem. Basically outlines a point charge that's going around in a circle because it's being in a Cartesian coordinate system, because it's being acted on by a magnetic field. So this part 1 here asks us to find an expression for the frequency. So I diagrammed basically what's happening. So this point charge is going around in a circle about the origin, and it's going in that circle because a magnetic field is acting on it. And we know, okay, so let's just say, first off, we know that frequency, because of physics 207, is equal to velocity divided by 2 pi r, which makes a lot of sense because the frequency is just equal to the velocity divided by 2 pi radians. Obviously, 2 pi radians in a circle times the radius, or the distance out to the point where that velocity is being taken. So the frequency is equal to the velocity of that charge going around in a circle divided by 2 pi r. And we also know that the force inward, remember that because this is circular motion, and that charge wants to go in a straight line, but that magnetic field is always acting towards the center of the circle, so the force is going towards the center, is equal to qvb, and it's also equal to mass times velocity squared over r. So we can just set these things equal to each other. This is actually, wow, I just realized this is actually really similar to what we did in our lab the other day, trying to find the ratio of E over m using the E over m apparatus. Anyway, so because these expressions are both equal, we can just set them equal to each other and solve for r. So once we have r, then we can plug r back into here. So we know that I use this kind of curly f as frequency and this capital F as force. So once we have the expression for the radius in terms of mass, velocity, charge, and magnetic field, we can plug that into here. So we have the frequency is equal to v over 2 pi times qb over mv, and you know that the v's can just cancel. So yeah, the v's cancel, and it leaves us with this expression right here, which is really nice because it's so simple. Yeah, okay, so part 2 is really interesting. It asks what would happen basically if you turned on an electric field that was going upwards in this system where this point was traveling around in a circle on the xy plane. What if you turned on an electric field that was pushing the charge up in a z direction? So basically, to do this, we have to find an expression for in time of that delta z, or that how much that charge is going to go up in how much time. So we know that again from 207 that it's delta c in our case, but delta x is equal to velocity initial time times 1/2 at squared, or velocity initial times time plus 1/2 acceleration times time squared. And we also know that F equals ma and qe, which this is last semester, but this is kind of what we're going to be using here, because this is the charge q times the electric field. So we can solve for acceleration by just saying ma equals q times e, and then acceleration equals qe over m. So then we can plug this into, and we know the velocity initial, just imagining, this is purely in the z direction, so even though it has a velocity in the x and the y direction, in the z, if you were looking at it where the z was up, it would be not moving at all, because it would just be going in a totally flat circle. So velocity initial in the z direction is 0, so we can just neglect this and say it goes to 0. But we can plug this in for a, so we get delta z is equal to at squared, or delta z is equal to qe divided by m t squared over 2. So, and then we know from the problem that we can just set q, m, b, v, and e all equal to 1. So that's really nice, so that this q, e, and m all just goes to 1. So this is just 1 times t squared over 2, and then we just have t squared over 2. And that's the expression of delta z as a function of t time, which is again nice because it's so simple. And you can also tell from this expression, from this this function of time, what the graph is going to look like, or what the plot, the three-dimensional plot is going to look like. And you can just see from, well, I plotted it on Wolfram Alpha as well, but you can just see from this that as a little bit of time goes by, it's going to be, the spirals are going to, it's going to be this like kind of a spiral motion, but the spirals are going to be really close together. But as t grows, this numerator will grow a lot faster than the denominator, which is, well, actually the denominator won't grow at all because it's just 2. But this will start growing faster and faster and faster because of the squared value. So if t is 2, the difference between 1 and 2 is going to be a lot less than the difference between 9 and 10 because of this squared. So I plotted it on Wolfram Alpha in a few different ways. So can I make this bigger? Oh, no, it's kind of weird. So this first one, I think I set the upper bound as something like 8 or 7 or something like that. You can see it kind of doing what I said, going around more tightly and then going up as time t gets larger and larger, it flies out and gets, the frequency is less and less. With the upper bound a little bit bigger on this one. This is where the upper bound is 10. It's a little bit more interesting. And then the last one, I think I made the upper bound, what is this? 25. So yeah, this one you can see, this plot you can see really well how it's really tightly wound at the bottom and then it goes out and longer and longer and longer and longer at the top. So this is what the motion of the particle would look like if you applied a uniform electric field and upwards in the z direction. Okay.